Hey everyone, I hope you're doing well today. In this video, I'm going to be talking about implicit differentiation. You know you're going to need to use implicit differentiation when there's no easy way of writing your equation with y isolated by itself on one side of the equation. Take a look at these three equations here. Since y is already isolated on one side in all three equations, you can just use all the differentiation rules that you know to differentiate the right sides of these equations. Whether it's the power rule, product rule, quotient rule, or chain rule, you don't need implicit differentiation for these types of equations. However, you're going to need to use implicit differentiation when you have equations that look like this. To differentiate the equations that look like the ones on the right, we're going to need to use implicit differentiation. While I totally get that you might not like learning about implicit differentiation, there's nothing stopping you from implicitly clicking that like button. Clicking that like button will help the YouTube algorithm push this video towards people who might also be looking for some help with this topic. Now it's time to grab some paper, something to write with, and let's do some math together. In example 1, let's look at this equation where we have y cubed minus 4y squared is equal to x to the 5th power plus 3x to the 4th power. Throughout this video, whenever we find the derivative of a y term, we're going to attach this dy dx next to it. And each time we take the derivative of an x term, we're going to attach a dx dx to it. I'm going to start by writing d dx of the entire equation. This just means we're implicitly differentiating this equation in respect to x. Taking the derivative of y cubed, we're going to use the power rule and get 3y squared, and we're going to put this dy dx next to it. Next, we're going to differentiate this negative 4y squared in respect to x, and using the power rule again, we get minus 8y, and throw that dy dx next to it. Now let's find the derivative of x to the 5th power in respect to x. Once again, using the power rule, we're going to get 5x to the 4th power, and we'll throw that dx dx next to it. And finally, finding the derivative of 3x to the 4th power, we'll get 12x to the 3rd power with this dx dx next to it. It's really important to remember that when you're finding the derivative of these y terms, you write dy dx next to each of their derivatives. And likewise, when you're finding the derivative of these x terms, you stick these dx over dx's next to their derivatives. While you can technically skip writing the dx over dx because it's just equal to 1, I'm just going to be writing it throughout these examples to be extra clear. Let's see how we can simplify this a bit. At this point, it's important to remind you that we're actually solving for this dy dx. dy dx represents a derivative of the entire equation. Since dy dx is the GCF of the terms on the left side, let's factor it out and write dy dx times the quantity of 3y squared minus 8y. If you were thinking about maybe factoring out a y also as part of the GCF, you technically can, but we're not looking for y, we're just looking for dy dx. Now let's see if we can clean up the right side a little bit. Since these dx dx's are just equal to 1, we don't need to write them since anything times 1 stays the same. Simplifying this, we get 5x to the 4th power plus 12x to the 3rd power. Now that we have one of these dy dx's instead of two of them, it's time to isolate it. To do so, we can divide both sides by 3y squared minus 8y. On the left side, this just simplifies down to 1, and we're left with dy dx, which is the derivative, and that's equal to 5x to the 4th power plus 12x to the 3rd power over 3y squared minus 8y. Using implicit differentiation, this is our derivative. In example 2, we have the equation sine of y squared minus cosine of x squared equals cosine of y squared plus sine of x squared. For starters, let's establish that we're going to differentiate everything in respect to x. Let's start by taking d dx of sine of y squared. Using the chain rule, we're going to get cosine of y squared times 2y dy dx. And now taking d dx of negative cosine x squared, we're going to have to use the chain rule again and get sine of x squared times 2x dx dx. Over to the right side, we'll take d dx of cosine of y squared, and using the chain rule, we're going to get negative sine of y squared times 2y dy dx. And finally, taking d dx of sine of x squared, using the chain rule one last time, we're going to get cosine of x squared times 2x dx dx. Now that we've taken the derivative of each term with respect to x, let's clean this up a bit. Just rearranging this a bit, we can write 2y times cosine of y squared dy dx, and cleaning this up a bit, we can drop this dx dx, since it's just equal to 1, and we'll get 2x times sine of x squared. Looking on the right side, we can rearrange this term and write negative 2 times sine of y squared dy dx, and looking at this final term, this dx dx, we can drop and write plus 2x times cosine of x squared. Now that we've cleaned it up a bit, remember what our original goal is. While the dx dx's always simplify down to just being 1, our goal is to isolate this dy dx and solve for it. To get both terms that have the dy dx on the left side, we're going to add 2 times sine of y squared dy dx to both sides. In the same step, I'm going to move this 2x sine x squared to the right side by subtracting it from both sides. After doing some rearranging, we get this equation right here. Now that we have both of the dy dx's on the left side, let's factor it out. Factoring out the dy dx, this is our new equation. Now that we finally only have one dy dx, let's divide both sides by 2y times cosine of y squared plus 2 times sine of y squared to completely isolate this dy dx. On the left side, this will just simplify down to 1, and we can write dy dx, or the derivative, is equal to negative 2x times sine of x squared plus 2x times cosine of x squared over 2y times cosine of y squared plus 2 times sine of y squared. This is our derivative using implicit differentiation. For example 3, we have the equation 3x squared plus 5xy squared minus 4y cubed is equal to 8. If you'd like to try this problem on your own, pause the video now. Otherwise, let's work together on solving it. Just like the last two examples, let's take d dx of the entire equation. We're going to take the derivative of each term with respect to x. Taking d dx of 3x squared, we'll get 6x dx dx. And taking d dx of 5xy squared, we're going to have to use the product rule here. From that, we're going to get plus 5x times 2y dy dx plus 5 dx dx times y squared. For this 4y cubed, we're going to get minus 12y squared dy dx. And as usual, for a constant, we're going to get 0. Now let's clean things up a bit. Go ahead and get rid of these dx dx's, and we'll get 6x plus 10xy dy dx plus 5y squared minus 12y squared dy dx is equal to 0. Now this looks a little bit more simplified. Let's work on just getting one of these dy dx's and isolating it. First, we can subtract 6x from both sides to move it to the right side. Then we can subtract 5y squared from both sides. Both of these are going to cancel out on the left side, so we'll have 10xy dy dx minus 12y squared dy dx is equal to negative 6x minus 5y squared. Factoring out the common dy dx's, we can write dy dx times the quantity of 10xy minus 12y squared is equal to negative 6x minus 5y squared. Now that we finally have one dy dx, let's isolate it by dividing both sides by 10xy minus 12y squared. This is just going to cancel out to make 1, and we can write dy dx is equal to negative 6x minus 5y squared over 10xy minus 12y squared. And there you have 3 different examples of using implicit differentiation. If you found the video helpful, please let me know in the comment section below and give the video a thumbs up. As always, keep up the good work, and I'll see you in the next one.